Good day, everyone. For the last topic under curvilinear motion of particles, I will discuss about relative motion of two particles using translating axis. So before, under the rectilinear motion, the absolute motion of a particle has been determined using a single fixed reference frame. So that was what we discussed before under the rectilinear motion, which we also tackle about the relative motion, but it is determined using a single fixed reference frame. But there are many cases, however, where the path of motion for a particle is complicated. So, so that it may be easier to analyze the motion in parts by using two or more frames of reference. So let's describe first the position. So considering two particles, which is represented by A and B, which move along the arbitrary paths. So let's have this first particle, which is the particle A, and the second particle, which is your particle B. And these two particles have a different path. So for particle A, say this is the path for particle A, and for particle B, this is the path for the particle B. And the absolute position of each particle, which is represented by vectors RA and RB, is measured from the common origin O of the fixed XYZ reference frame. So for us to determine the vectors RA and RB, let us define the fixed reference frame. So let us say this is your fixed reference frame, or in layman's term, your fixed origin. So from that, this is your XYZ reference frame. And from the fixed origin going to particle A, it is represented by vector RA. And from the fixed origin going to particle B rather, that is your vector RB. So these are your absolute position of each particle that is measured from the common origin O, or from the fixed origin. The origin of a second frame of reference, X prime, Y prime, Z prime, is attached to and moves with particle A. So we will have another reference frame which is attached to your particle A. So I changed the color so that it will be clear, or it can be seen clearly, the reference frame X prime, Y prime, and Z prime. So this is your another reference frame. So this is your X prime, Y prime, and Z prime. So this reference frame is your translating axis, and the axes of this frame are only permitted to translate relative to the fixed frame. So the position of B measured relative to A is denoted by the relative position vector Rs of B relative to A. So from the particle A going to particle B, that is your vector, or your relative position vector Rs of B relative to A. So using vector addition, and from the figure, as you can see in the figure, what we had is a triangle. And as you remember in statics, the three vectors shown here can be related by the equation Rs of B is equal to Rs of A plus Rs of B relative to A. So this equation is based from the definition of vector addition. So from that, from this equation, we can also describe or define for the velocity and for the acceleration. For the velocity, an equation that relates the velocities of the particles is determined by taking the time derivative of the previous equation. So that is from the position from the previous slide. So that is the vector v of b is equal to vector v of a plus vector v of b relative to a, which states that the velocity of b is equal to the velocity of a plus, which is vectorially added rather to the velocity of b with respect to a as measured by the translating observer fixed in the x prime, y prime, z prime reference frame. So here your vector v of b that is equal to the derivative of your vector r's of b with respect to time, and your vector v of a is equal to the derivative of vector r's of a with respect to time, which is referred to us as the absolute velocities. And since they are observed from the fixed frame, whereas the relative velocity, which is the vector v of b relative to a, is equal to the derivative of your vector r's of b with respect or with relative to a with respect to time, is observed from the translating frame. So again, this equation was derived from the equation from the position from the previous slide. And for the acceleration, the time derivative of the previous equation, which is described from the velocity, yields a similar vector relation between the absolute and relative accelerations of particles A and B. So that is the vector A of B is equal to vector A of A plus vector A of B relative to A, where the vector A of B relative to A is the acceleration of B as seen by the observer located at A and translating with the x prime, y prime, z prime reference frame. So before we had discussion on sample problems about this topic, let's discuss first the procedure for analysis. So when applying the relative velocity and acceleration equations, it is first necessary to specify the particle A that is the origin for the translating x prime, y prime, z prime axis. And usually this point has a known velocity or acceleration. So it's better that you first specify the particle A as your origin for your translating axis, which is defined as the x prime, y prime, z prime reference frame. And since vector addition forms a triangle, there can be at most two unknowns, which is represented by the magnitudes and or directions of the vector quantities. And these unknowns can be solved for either graphically using trigonometry, which can be solved by using law of sines, law of cosines, or by resolving each of the three vectors into rectangular or Cartesian components, thereby generating a set of scalar equations. So actually this kind of way for you to solve the unknowns was discussed on the first topic in statics of rigid bodies or engineering mechanics 1. So the next videos, I will discuss about sample problems about relative motion of two particles using translating axis.